and then there should be time to work on stuff afterward. So yeah, I want to talk about chapter 4. Chapter 4 is on data types in Python, and there are quite a few. If you've taken another programming class, you know what the word type means, but if you haven't, that's okay too. I will teach it to you from scratch. So this is about chapter 4. Please go and start reading chapter 4 if you've not gotten to it yet. All right, it's time. So yeah, I don't have a ton of slides, just have more examples really today. So I just want to show you that when you use things in Python, it knows the kinds of things that you're using, and that's a very vague statement, I know. So when you use a number, for example, Python understands that you typed a number and you want to do math with it, kind of. When you type things between quotes, Python understands that you typed text and you want to do text-based things with that. It's like you can't do number stuff on text, for example. There's a difference between the two. So yeah, let me show you those ideas. And Python always knows the type of thing. The type of something that you have kind of shows you what you can do to it. All right, so let me fix the pen. There we go. So like when you type 42 in Python, it knows that that is a number, and you can do number stuff with it. All right. For example, like we've learned about functions too. Like we know that we can call functions, but we can't do math on functions. All right. But 42 is a number, and you can do math on numbers. And the kind of number that it is, it's called an int. 42 is an int, the type of 42. When you type it into Python, it knows that you typed an integer, a whole number. That's what that means, and it knows the difference. All right, so that's int, and Python really does know. So let me go to today's first notebook. So if you type 42, you can do math stuff, of course, with 42. 42 evaluates to 42. You can do 42 plus 42 again, but it always knows there's a special built-in function to Python called type that you can like give to something. You can ask it, hey, what in the world is the type of this 42 thing? It really is keeping track, and it knows that that thing that is 42 is an integer. It's a whole number, and that's what int means. Okay, so there's that. What else? Yeah, we know that we have functions as well, right? Functions are things that we can call. Python knows that there's a type of thing called function, like things that you're able to call. It's like we learned the round function, right? Round pi, 3.14159 to like round pi to 3 decimal places. It does the work, but like what's the type of round? You can ask that. That's the name of it. It is a built-in function into Python. That's what it knows. Okay, so it really does know the difference. And also the numbers with decimal places are not the same as whole numbers, right? Numbers with decimal places are not just integers. So the type of like 42.5, not the different type, it's called float. All right, so float is short for floating point, which just kind of means that it has a decimal place, and that decimal place can be, it's like secretly stored in scientific notation, so the decimal place can float around. You can think of it that way. So yeah, that's 42. Moral of the story, 42 is an int. Like the round function was its type was function, and like 3.14, the type of that kind of number, a number with decimal places, is a float. All right, so they're all different things, and Python knows secretly. It's keeping track of what's what. All right, so with ints and floats, you can do math, of course. Like you can make it happen. It's like 1.5 plus 2. You can do math on both of them. It'll just like convert it to whatever it needs to be. Notice that, all right, we have decimal places. So the answer of a float plus an int became a float again. You can think about it that way. I hope that makes some sense. Let's see, what else? There's that one. And yeah, sometimes when you do math on like division, especially if you do math on integers, on ints, it gives you a float back. The 0.0 appears because usually when you divide, it doesn't go in cleanly all the time. So it just like defaults to giving you a float back. So the types are secretly important, and I want you to start keeping track of them. All right. Are there any questions about that? You kind of understand like there is a difference between the kind of thing that is 42 and the kind of thing that is 42.5. And same with like the name of a function. It's a different thing. It's something that you can use in a different way. Yeah. So that's fun. What else do I want to do here? When you, oh gosh, do I want to do it that way? No, I'll show that to you in a second. Yeah, so I'm still talking about integers. You can have variables as well, and the variables are the type of whatever thing is stored inside of them. So for example, let's make a variable x, right? Set it to hold 42. And then I can mess with it and be like x times 2, something like that. So I can do math on whatever was in x, and the thing in x is 42, and that's an int, right? So the type of x then is an int, if that makes sense. Type of x is an int. It's holding 42. 42 is an int. Does that make sense to us? That's what's going on there. All right. So yeah, that was the type of a variable then is the type of whatever thing it's holding. So that's what was happening there. What else? What else? You can do disgusting things to variables. You can say, you know what, x is now 3.14. You can do that. Once I run that line, it's going to change what's in the x box, right? The variable now holds 3.14. It holds pi instead. And the type of 3.14 is no longer an int, is it? It's a float. So the second I change the kind of thing that's in the x variable, the type of the x variable then changes back to something else. All right, there's that. And yeah, let's see, what else was I trying to say here? The things that get stored in types, yeah, they just kind of act differently. So floats in particular, they're secretly stored. The reason it's called float is because it's secretly stored in scientific notation. And so you can type scientific notation to Python if you wanted to represent the idea of like the number 5 times 10 to the 6th power. The shorthand for it is the letter E. So you say 5E6. That turns into this idea of 5 times 10 to the 6th power. The E just kind of means that. 5 times 10 exponent to the 6. Something like that. That's how you can think about it. So that's a quick way to get scientific notation-y numbers into Python. So 5E6 is 5 times 10 to the 6th power. That E means times 10 to the something. And so it's easier to type than trying to figure out how to do a superscript. But you know how to do power computation. It's a double star, right? So that's just a quicker way to do that. There's that, and that's float stuff. This is syntax that creates a different kind of float. All right. What else? What else? I want to talk about precision as well. So here's something weird. Gosh, what's the best way to tie this to? So let me count how many I was doing here. 1, 2, 3, 2, 4, 6, 8, 10, 12, 14. Yeah, it's 16. So let me type this. 0. I'm going to type 0. A bunch of 5s. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. 16 5s, all right? And then I'm going to subtract from that the same number with some more digits after that. All right? So the result then, because the one on the right's a bigger number, yes? The result should be a negative number, right? I should see when I press Shift-Enter or the play button, I should see a negative number in the output, yes? Because the thing on the right was bigger. I took the same number and I added some more decimals at the end of it. But this is float math. I'm going to get 0. In Python, floats are not perfectly precise. They're storing their numbers secretly in scientific notation, and you only get 16 digits of precision. That's all you get. So floats, unlike ints are perfectly precise. They'll always remember. Floats are not. So the type really matters, see? Floats are not perfectly precise. You only get about 16 decimal places of precision is what it's called. So if you try to type more after 16 decimal places, it kind of forgets about them. That was too much information. It couldn't store that in the memory that a float can take up. Okay, that's different from ints. Okay, ints are precise. You can keep everything around as an int. That's fine. It's happy. So yeah, interesting things. All right, interesting things. And this shows up when you're doing math on floats, because floats are not perfectly precise. You're not always going to get what you expect to see. So like if I do the square root of 2, one way to type that is 2 to the 0.5, right? There's the square root of 2. What should the answer be for the following? Times that. So if I multiply the square root of 2 by itself, what should the answer be? Just 2, yeah, right? Square root of 2. times the square root of 2 is 2 to the 1/2 times 2 to the 1/2, like the 1/2s become 1, right? So I should see 2, but because of the imprecision, because I only get about 16 decimal places of precision, that's not perfectly the square root of 2. It's a little bit off, slightly off. If you round it, it's not a big deal, but if you try to look at the full representation of the number with all the decimal places of precision, you're going to get a little bit of an error there. You see that? It's not a perfectly precise answer. That's what floats are for. They give you like 16 decimal places of precision, and usually that's good enough for most purposes, but sometimes it's not. Sometimes you should be rounding, sometimes you should be using a different kind of, like a library that gives you perfectly precise numbers to even more decimal places. There's things involved there, all right? So that's my story about ints and floats. Are there any questions about those types? Those are our two numerical types. They work a little bit different. Floats are weird. A little bit weird. So yeah, just shout out if you can think of any questions about that stuff. The next type I want to talk about is a type that can hold text. So a text type is called stir. When you give things, any information between quotes, either single quotes or double quotes, Python doesn't care, that creates a stir type. And that's short for the word string. So string is the full name of that type. So if you type things between quotes, you get a string. So if I say, what's the type of hi mom between quotes? It's a stir. It's a string. You think of it as like a string of character beads on a friendship bracelet or something. That's the type of that. And also between double quotes. Python doesn't care. As long as you're consistent, you can be like, hello world. The type of that. Still a stir. Okay? And the type of things dictates what you can do to those things. So there's a plus operation on stirs, but it's not mathematical. So for example, here is I'll do the stir data, and I'll add it to the stir, with double quotes for fun, space 8. It will create the bigger stir with all the characters together. Does that make sense? That's a plus on stirs. It's not a mathematical plus anymore. It's adding characters now. Okay? So there's that. Sometimes it really does matter if you need to use double quotes or single quotes, because you can't like type something with contractions and single quoted stirs. You can't be like, can't do this with single quotes, because Python's going to get very confused about where does this stir end. It'll think that the stir ends right there. Does that make sense? You'll think that it ends on that third character right there, which was supposed to be a character inside of the string, but it's meant to end the stir as well. So that will give you an error. It's like invalid syntax. I wasn't expecting a T there. I thought the stir was over. I thought the string was over. So you have to use double quotes. Or you can do something special, which I'll show you later. So sometimes your hand is forced. Like you needed to use double quotes to make that work. Okay? So, dun, dun, dun. So yeah, or you can't do this with single quotes is what I was trying to say. With single quotes. A bunch of them. So yeah, otherwise we'll get an error. And yeah, the kinds of, you can do math on stirs, but it's not normal math. So let's see, what else do I want to say? Dun, dun, dun. That is most of it. Yeah, you can't quite get what you want all the time. Let's see. How do I want to show this to you? We'll just do it together live. So there we've got, yeah, that's stir in a nutshell. And kind of the last one that I want to show you is comparisons. Comparisons will give you something. They give you some answer that's either true or false. And I'll show you those in a second, like yes or no. And the type of those things is a bool. Bool is short for Boolean. It was a person's last name. So you can ask Python, hey, is 4 less than 5, for example? And the answer is going to be yes, and that's a true answer. So the type of that, type of whatever that result is, the type of true it's called a bool. It's a yes or no answer. All right. So false would be no, and I'll explain that more later. So yeah, I think that was all that I wanted to say about this slide. Are there any questions about the types of different things? All right, because sometimes you have a type and you don't want it to be that type. You can always convert by using the name of a type as a function. So say you have the int 42, you want to like make it like you add the characters to a bigger place, a bigger string. You can convert it to a str by calling a function that's the same name as that type. You can say str 42. It gives you back the string 42. It will give back for you this. Boop. It'll give you back the string 42, which is just characters now, but you can add those on later. So you can do that. If you have a str, but you really wanted to do like math on it, you can convert it, if it had numbers in it, you can convert that to an int by calling the type that you want as a function. All right, you can do that. You can also convert floats. Like this was an int, you want to make it a float, make it 1.0. You just call the name of that function, call the name of the type you want as a function. It'll make 1.0 for you. Does that kind of make sense? So let me show you where you might want that. So for example, if you want to print something out, like the answer is colon space, like 2 plus 2 is what you really want to show, this won't work because you know that the plus operation doesn't make sense to add a str to an int. Do you see how it's saying that now? Cannot concatenate. Concatenate just means add the characters of a str and an int. See that? So it's complaining, and you know those words now. Instead, you need to turn this answer of 4 into characters, into a str so you can add the characters together. So that's what we want. You can say, give me that, please, as a str. So you call it, it'll do the work, make 4, then it'll convert that to a string, quotes 4, and that makes all the difference, right? So now I can add that. Now I can say, all right, the answer is the str version of 2 plus 2, and that will create the string 4, which it will add it properly and be happy because the types are the same now. Are there any questions about that? Do we see that? See how that's necessary? So yeah, sometimes when you have a str, or when you have an int, you really wanted a str. If you wanted to build up a bigger string to output to somebody, maybe. And likewise, you sometimes want the other direction. Like if you have some strs that are really representing numbers, you know that the plus is not going to make 84, is it? The plus is going to make 4242. See that? When they're strs, you're just getting characters right after each other. If you wanted the work done, really in math, you need to convert the types. All right, I had the quotes 42, I had the string 42. I want it to become an integer, please. Make it an int. And then I want to do math with the other one as well in the same way. Like, all right, it was a str, it was just characters, but I want to treat it like a number. So make a number out of it, please. Then I can do the math on numbers, because now on this side I have the int 42, I have on this side the int 42, and then the plus on int does math, does whole number math. Okay? You see how that, it's like this is a very important 2 cells to understand. Are there any questions about why you need those, why they're doing different things? The types really matter. The plus is overloaded for strs, the plus is overloaded for ints and floats. They do completely different things. Sometimes you want one, sometimes you want the other. So, yeah. With that in mind, I want you guys to try some stuff so you can play around with it. I'd really just want to know, I kind of just want to know your intuition here, so try to come up with some good guesses, really. But here are 3 questions for us. 1, 2, and 3. I'd like us to go to the by clicker page, please. And make sure to do that attendance. I'll stop that after this question. So let's do by clicker, and I'll start it. But I'd like you guys to get into little peer instruction groups, say hello, talk about your 3-day weekend, introduce yourselves if you're sitting next to somebody new this time. But what I want you to think of is the answers to each of these 3. What do you think happens when you try to convert a float into an int, the str 42 into a float, and the str hello into a str again? What do you think happens? Do you think it's an error? Not an error, like it, and it's fine, or not an error, but you get a result that you weren't expecting. So like not an error, like B is like not an error, and the answer still makes sense. And then C is like not an error, but it doesn't make sense at all. So see if you can see what your intuition tells you, and you can check it out on your own if you want to try it. But enter in your answer to 1, but have your answers for 2 and 3 ready, please. And I got the timer ticking. So yeah, take a few minutes to talk about these ideas and think about what it all means and ask me any questions. Okay? Maybe a few minutes to think about it, maybe 3 minutes or so. Are you trying to help the class? Oh, okay. I think I'm willing to change it. But there's a lot we got to do with it, right? I'll come to you. But the last one's kind of weird. It's already Sterling. $864. Oh yeah, the canvas is not going to ask you for like an hour. But it has to be laser computer versus cognitive. Our class was at office class. We're using your last name underscore username, the password is the same. So as your password, well, you check it. That's where you did the password. Watch when you get added to the campus, you can watch the other lectures. Assignments and things, but we've got an assignment due today. Then another two on Friday. I think I'll give you maybe till the end of Sunday to get everything to get caught up. So it's all good. Yeah, good. All right, friends. Let's see. Until Sunday at. See if we can get caught up. All right, sorry, I was doing stuff. Let's see what we're thinking. Let's see what we're thinking for the first one. So the answer for the first one you got in there already. What do we think? Oh, we're not quite sure, which is good. Do we think that it's? I guess it depends. Like, does the answer that we get back make sense? What was the answer that we got back when we tried that one? Did we try it? How do you turn a float into a whole number? If it's 2.5, you kind of have two options, right? There's like two normal sounding options. Either it's 2 or it's 3. And it just so happens that the answer is going to be 2. All right. The answer is going to be 2, which is a little bit odd. And so maybe the answer is C for a lot of us, but some of us who have come from another programming language have maybe seen this before. But to turn a float into an int, it's not going to round. It's weird. It's just going to chop off the decimal places because it can't hold them. It's going to chop off, even if it was 2.99, converting that to an int is still going to be 2. It's just going to forget about them because it can't hold those decimal places. It's not even going to try to round. I hope that makes a little bit of sense, but that's what's going to go on. All right, what about the next one? What about question 2? Give that a try. What did you guys come up with that? What's going to happen when you say float of the stir 42? Can Python figure it out? Enter in your answer on the by clicker page. What did you guys come up with? Is this going to work? Whee. I'll give you another 10 seconds. You should be ready with this answer. What do you think happens? You can try it too. Does Python know like if you type float of 1,999,000, if you type that out, does it know what you mean? Yeah, it's going to give you an error because it has no clue. Especially like you have to bake in like all of English, right, for it to be able to do this kind of thing. That would be crazy. To like give an AI to Python, that would be way too much. So that's going to give you an error. Float of 42. You do have to have the dash. That's the correct way to spell it. So I cannot convert a string to a float. It has no idea. It's only going to work if there were digits. If it was like the str 3.14 between quotes, it would be fine with that. But if you try to spell it with English, that doesn't make sense to Python. Okay. And then the last one, what did you guys get for this one? What happens when you say stir of hello? What does it give to you? Is it going to be an error because it's already a stir? That's an option, right? Do you think it will, let's see, give you the stir, like it adds some quotes within it or something, make it look a little bit different every time you try to convert it to a stir again? It adds more quotes maybe. So maybe that would be C, like it doesn't make sense. Or like, does the answer make sense? What'd you guys get? All right, we think it kind of makes sense, and I hope it does. So you'd be like stir of hello, or sorry, excuse me. Yeah, it was hello, right? Yeah, hello. It's like it's already a stir. It gives you back the same thing. I think that makes sense to me. I hope that does to you too. Are there any questions about these examples? Do you see what's going on there? It's like for this one, it was that. For this one, it's like, is this somehow going to turn this into 42.0? No, it doesn't know enough. For this one, it's like, it's already a stir. Does it like give you an error? Does it add some extra quotes? Was one idea. Or does it just give it back to you the same way? And that was what it actually ended up doing. That was the answer, wasn't it? So yeah, that's what went on, and I hope you see it. All right, so weird stuff going on. Are we ready for comparisons? Any questions about this stuff? Because that's my next slide, and I think yeah, let's go there, and yeah, we'll make things work. So I need to remember to give you those in a second. But comparisons are these things. There's operations to compare things in Python, and here are the different ways to do it. If you want to ask if something's less than another thing, you just type the less than. Same with greater than. It's really, really hard in Python to be able to type like this character. It's a Unicode character. It's not on your keyboard. And so they've just gave up, and they're like, type the less than and then the equals to mean less than or equal to. All right, so you do that. And greater than or equal to, then we got equality check and disequality check, and I'll show you all of those. All right, so here is what's going on there. So 2 is 2 less than 3. The answer is yes. The answer, it gives it back to you as either true or false, and those are bools, Boolean things, yes or no answer. So true means yes in Python, and false means no. Okay, that's what's going on there. Hey, is 3 less than 2? The answer is no, so it says false. That's how Python tells you no. It does the work, and it's going to try to figure it out for you, okay? So greater than or equal to, less than or equal to, you guys can see what's going on there. Equal and not equal to are a little weird looking, all right? So you can't do this. You can't be like, hey, Python is 4 equal to 4 and just type 1 equal sign, because we know that equal sign is overloaded, don't we? This is going to be like, no, I don't know what you're talking about, because it thinks you're trying to assign a value into a variable. because that's what the equals does, right? That's what we normally use equal for, and so that's been taken in Python. We can't use a single equals to mean check for equality, because that means assign a value into a variable. It's like maybe it meant double equals. So that was the trick. What we've done is we've made two equals. That's what they do in most programming languages. You use two equals to do an equality check. All right, give me a yes or no answer. Is the thing equal? Is it not equal? So hey, is 4 equal to 4? The answer is yes, and it's a double equals to do the check. All right, so don't forget, it's double equals to check for equality, single equals to assign a value into a variable, right side into the left side. Okay. And then likewise for this not equals to check, this is this idea. Hey, is something not equal to another thing? So that kind of character, but again, that's really hard to type inside of a computer. So they change it into an exclamation point and an equal sign. So you read the exclamation point as not. It's like, is it not equal? Hey, is 3 not equal to? Yes, true. Hey, is 2 not equal to 2? No, it's equal, so no, false. That's the kind of examples and things that you get there. Let's see. Is 2 not equal to 3? Yes, it's not equal. It's a little hard to wrap your mind around, but that's kind of how that works. And yeah, the reason, again, we have to use double equals is because we've already used the single equals for a different thing. It's this idea of assigning a value into a variable. X equals 42. That makes that box in memory that holds 42, and you call it X. So if you want to check for equality, it's double equals instead. All right. Those are your main comparisons in Python. Are there any questions about them? Kind of see that they're mostly the same as math, right? All right. Yeah, if we're good, I want to show you that there's other things that you could do. You can chain comparisons, like in math. Maybe you've seen, hey, is like 1 less than 2, and also is 2 less than 3, and you've seen this typed this way or written this way. Just like to make sure that this chain of equalities is all true. Hey, is this all true? Is 1 less than 2 and 2 less than 3? Yes. So you do a chain of inequalities just like that, and Python is fine with it. It works just like you would write in math, if you've seen that before. That's the thing. You can check for equality on things of other types, like, hey, are these two strs equal to each other? Absolutely. It's happy. There's no issue with that. It's also a little weird in that, let's see, you can compare strs, like, hey, is hi less than mom? And the answer is yes, and the reason why is because in Python it's doing comparisons on text in alphabetical order, in dictionary order. Like, would hi come before mom in the dictionary? Yes, that's what it's saying there. Usually you're not going to care much about that in this class, but like that's why it's doing that. And again, the idea of true and falses, those are bools. Like, what's the type of true of all these answers we've been getting? They're called bools. True is a bool, false is a bool. Those are the only ones. Yes?
So what if like it's not the comparison of hi and mom, it's not comparing like how many characters are in each one?
No. So like the less than part?
Yeah.
Yeah, it's just asking, hey, does hi come before mom in the dictionary?
Oh. Okay.
That's what...
Characters, like if those characters in there, that's true.
Nope, that would be, once we get to like the len function, that would be a different idea. It's like, is the length of hi less than the length of mom? It's a different question to be asking. Like, are the strs themselves, like, is hi less than mom? It's doing dictionary ordering. Yeah, good question. Other questions? Yeah, these are just things you pick up, and they'll make sense eventually. Let's see. Yeah, let's talk about some random ideas about things that I want to show you. Let's see. This is my miscellaneous section now. Miscellaneous things Lawton needs to teach you. But are we ready for that? Like, does everything else that we talked about make sense? So the idea of there's a bunch of different things. They're all different types. Python remembers the types of things, and the type of something dictates what you can do to it. And comparisons are ways to check for, hey, is something less than another, greater than another, equal to, not equal to, for some definition of less than, right? It's different for strs than for ints and floats. Okay. So yeah, if we're good with that, there's some different things that you can do on strs that I want to show you. There's an operation called dot upper. So like if I had the string data8 like this, lowercase, you can say dot upper on it to change all of the characters that are possible to be made uppercase to uppercase. So it's going to capitalize everything that it can possibly capitalize. If they were already capitalized, I'd keep them the same. That's kind of nice. That's the upper function. There's you better believe that there's a dot lower function, right? Dot lower operation. So there's that one. And there's also a dot replace that will be useful. So here's the standard example that they used in your textbook. I think it's cool. You got hitchhiker. There's a dot replace operation on stirs where you say like what you want to be replaced and then what you want it to be replaced with. So let's replace every time we see high with MA, it's going to turn hitchhiker into matchmaker, and I hope you see why. It finds this HI and it turns it into MA. It finds this HI and it turns it into MA. Does that make sense? That's an operation on stirs that kind of takes the stir first. It's a little weird. It's not really something fancier than a function. It's called a method, which is beside the point. But that the dot is like, hey, act on the stir, do something to it. Give me back a new answer based on it. Okay. So yeah, that's all that. What else? I want to do some math stuff with you next. So let's import. Remember, if I want to use a library that's made by somebody, I say import the name of that library. Now I can say math dot stuff to get access to it. So here's how you do that. Boop, boop, boop. Oh yeah, I promised to stop that. Dun, dun, dun. And so you can always say Python math if you want to learn more about that library. Like click on it. And you can see what's there. So like there's a bunch of different functions. The one that we talked about, there's the square root function. Where is the normal one? That one. You can always click on it to see more. Like what's square root? It's math.square root of something. Okay. So yeah, let me show that to you again. So math.square root of 2. Dun, dun, dun. That gives you the square root of 2 using the function defined in the math library. You gotta prefix it like that. So don't forget that. There's also some variables defined in the math library. It doesn't have to be just functions in a library. There's also some variables that are defined for us. There's pi, there's e, there's other things. So I can ask for what's math.e. That's a way to get that constant so that I don't need to make it myself. Math.pi, that's the pi variable living in the math library. Okay, so there's that. And next I want to teach you about weird kinds of rounding. There's the normal round function that's just baked in. It's not part of the math library. So we had that, like round pi to 2 decimal places. Like that's already baked into Python. But there's some other weirder rounding functions in the math library. There's one called floor, and then there's one called ceiling. It's a little weird. So there's floor and ceil. And the metaphor is you're shoving a number down to the floor, or you're pushing up a number to the ceiling. All right? So an example is worth a million words. So the floor function gives you back the largest integer less than or equal to the original number that you're giving. So I can say math.floor 2.71, let's say, or 2.72 if I want to do e correctly rounded. So if I press Shift Enter, what's going to do is it's going to round it down. It's going to shove it down to the floor. That's what this rounding function called floor is. It's always going to shove it down to the floor and give you back the number that is less than, the whole number that's less than or equal to it. Okay, the closest one. It's always shoving it down to the floor. If it's already 2, it's already a whole number, it's good. It's going to keep it there. So shoving it down, if it needs to be shoved down to the closest whole number if it's not 1 already. All right. And that's actually what the int function does. 2.72. The int operation on a float, it's always getting rid of any decimal places. That's the same idea as the floor rounding operation. It's always rounding down. Does that make sense? So shoving a number down to the floor. And then ceiling is the opposite. It's always shoving it up. So like if you had 3.14, it's going to push it up to 4. Does that make sense? That's the ceiling operation. Sometimes you need that. Okay? So there's that. Dun, dun, dun. And then here is a silly little question for you based on those ideas. Math.floor can be used to implement the idea of rounding a number to the nearest whole number. All right? So say I had a number x. Boop. And it held something, some number. Think about it, whatever it needs to be. Like it could have been, think about it like if it was 2.4, 2.5, 2.6, all these different values that it could have been. There's an operation that you could do here, this math.floor x plus some blank, that would round the number up if it's 2.5 or bigger, and round it down if it's 2.4 or like 2.49999 or smaller. Think about what could go in that blank if you had a number x and it held something to round x to the nearest whole number. Isn't that interesting? So try to just ponder that for like a minute, and then I'll show you the answer, because it is kind of hard to come up with. But think about what you might do. Like, what kind of operation that, like, if you gave it if x was 2.4, x plus something floored will make it 2. But if x was 2.5, x plus that same something floored, shoved down, will make it 3. Interesting. So think about that. Is somebody talking to me? Somebody sent me a message? Weird. It's hard if you don't see it, but it's a fun idea. It's a cute example of how you might implement the round function, at least for whole numbers. All right, the answer is, the secret is, what goes in this blank is 0.5. This will round a number to the nearest whole number. Think about it. If the number x was 2.4 and you added 0.5 to it, it would make 2.9. And then if you did the floor on it, the mathematical way, like the symbol for the floor operation in math looks like this, like you're drawing the floor around it kind of. And it's shoving it down, and it'll make 2, won't it? It'll make just 2, which is cool. If it was 2.5 or bigger, see what the plus 0.5 would do? It would make 3.0. Flooring that would keep it at 3. And anything bigger as well would keep it at 3. 2.6 would make it 3.1, right? Isn't that cool? I love that. And you just do like math.floor on something. It would give you, it's always going to chop off the decimal places. It's not going to give you anything bigger. So like, let's see. If it was 2.1, you'd end up doing like math.floor of 2.1 plus 0.5, so like, or 2.2 even, like 2.6. That would give you 2 again. That's kind of cool. Does that make a little bit of sense? I'm never going to ask you like to come up with this weird thing on a test. It's just like something cool that you can use that's in your library now. All right. I think that's what I wanted to say. Any questions about these math operations before I do one last thing for this set of slides? And we'll switch to some new ones. All right. So I told you that you cannot do some things, like if you wanted quotes, if you wanted contractions, you couldn't make a stir with single quotes, but I lied. You can't do it the normal way. It's like, I can't do this, right? This wouldn't evaluate properly. It's like, where in the world does the string end? It thinks that the string ends right here, right? Because that was the next single quote. It's like, oh, I think that the string started over again and it never really ended. So one way to fix it was to use double quotes instead. But what if you wanted to stir with double quotes, like you wanted to quote somebody who was saying a contraction, right? Could you just not do it? No, you can make it work. The secret is, instead of saying it like this, you put a backslash before the character that is going to ruin things. You put a backslash single quote inside of a single quoted string, this turns into a single quote inside of the string. It's called escaping it. You're escaping out of the problem area, all right? So that's what happens. It turns into the string can't with a quotation inside of it. And so that is how you can get around that. Same idea if you wanted inside of a double quoted string to type a double quote, you do a backslash double quote. Then it would be happy. It would make it part of it. It would make an actual character as a double quote. So that's how you do that. And then the last thing I want to show you that's miscellaneous is the idea of the len function. There's a function called len that's built into Python, and one of the things that it can do is it'll tell you the length of your string in terms of the number of characters. So you can ask for, what's the length of the hello string? Well, there's 5 characters in it, and it'll find that for you. All right. So those are my miscellaneous things for the day for this chapter 4. Are there any questions about any of that? Just some things that you're going to need on your next assignments. All right. If we are happy, I have one more set of slides to get through. It's another short one, so there's just 2 short chapters for today. This is chapter 5. It's on sequences. So we were able to make a variable now that holds like one thing, one number, one int, one float, one stir, right? What if we want like a bunch of things all at once? Like I want to store the numbers 1, 2, 3, 4, 5 all together. We need that ability. That's sequences. Okay, so let's make that happen now. So this is going to be chapter 5 stuff. Please read chapter 5. It's another short chapter. You'll get through it quickly, but it's time. And yeah, let's talk about the kind of sequence that we'll be using in this class. It's called an array. Okay, it's called an array, and it's a type. It's another type that can hold inner types. Okay, it's an array of something. It's like you can make an array of integers, an array of floats, an array of stirs. An array is a type that holds a sequence of values, and so it's a type that holds other types. All right, so you can make an array called like A, for example. Oops, there's like a bug in PowerPoint. When you first open it, it ruins your pens. You can make an array called A, and you can have it hold a bunch of stuff. A bunch of stuff all together. Have it hold like 42, 43, 44. If I can type and then make it legible. 44, 45, -1. And you can have them all be called A together. They're all as one big chunk. That's a sequence. That's called an array in Python. All right. So yeah, in this class, the arrays that we're going to use, they come from a different library. It's called the NumPy library. We're going to use that, and yeah, it lets us do like math on arrays. It's going to be really cool. Like you can add arrays to arrays, like that's a thing. So I'll show that to you. And then also, we were talking about tables just briefly last time. If you ask for like, give me just a column of a table, which is just the data values in a column of a table that was your data set, you can ask for that in the data science library and get it back. It's going to give it back to you as an array of all those things. So it's very important. So arrays are at the forefront of this class. They're at the heart of all the tables that we're using. So yeah, the place that we get arrays, the ability to make arrays, it comes from the NumPy library, but we can also, it's kind of like imported for us when we import our data science library. So here, let me make a new file for the day for chapter 5 stuff. I'll call it chapter 5 so you can get that easily. And I'm going to import all the data science stuff. And I don't want to say data science dot all day long. So I'm going to do it the fancy way. I'm going to say from data science, import star. And that gives me all the data science stuff without having to say data science dot this, data science dot that. Okay? And the secret way of getting stuff as an array is there's a function in the data science library called make array, make_array. And you can see more about that in one of our documentation pages. So it's here somewhere. It's not table stuff, it's array stuff. So array functions and methods, there's make_array. What you do is just a function, you give it a bunch of things, all the things that you want in your array, like this. You can call it a variable, and then it creates all those things in one spot as a big chunk. You can save it with one name. Okay? So it's make_array, and you can put whatever you want in there. 42, 43, 44, for example. And that becomes an array. It's one big chunk with a bunch of numbers. That's a sequence. All right? The type of that is an array. All right? So you can ask, like, what is the type of this thing? It is an array. It's from the NumPy library secretly. All right? So yeah, it's like NumPy. It's an n-dimensional array. It's just you can be like, it could be a grid technically if you wanted it to be, but it's just a single dimension right now. Okay, so you can make an array of numbers, of course. You can make an array of stirs, because that's also things that we can put in tables, right? You can say make an array of like Pokemon. Like I want an array of Pikachu, a bunch of stirs. All right, of Charizard, of Squirtle. I can use double quotes just for fun. So that's an array of names of things. I can save that into somewhere. I can say like Pokemon I like. That's a variable, all right? And that is an array of stirs, an array of strings stored in one spot. It's a sequence of things stored in one place so I can get them all at once. So Pokemon I like is a variable that holds that array secretly. Oops. So if I ask for what's in there, it's the array of all these things. So you can put a bunch of stuff together inside of an array, okay? So yeah, There's a lot of things going on there. Let's see, what else? What do I want to do? You can use len on arrays. You can say how big is that array. So there's 3 things in this array, right? What's the length of the array Pokemon I like? 3. Yeah. So just like for stirs, it works for arrays too. How long is the thing? What's the length of it? Okay. So with that, I want to teach you how to get the pieces, because like it's nice to have them all together, but what if I wanted like Charizard? I want to get that out. What's the second thing in the array? Go and get that for me. There's a way to do that and pick out pieces. So that is called indexing into an array, and all of your indices start at 0. That's a very computer sciencey thing to remember. Every index, if you want to go somewhere in an array, it's made up of a bunch of little slots called indices, and all the indices in computer science in most languages, except for the language R, I think, which is disgusting. It starts at 1. They all start at 0. All right. So if you want, like if this is your array, it goes 8, 6, 7, 5, 3. If you want the first thing, you go to index 0 always. The first thing is always at index 0. The second thing is at index 1. And that is something to get used to if you've never seen that before. All right. So if you go to index 1, you're going to get the second thing, not the first thing. The first thing is at index 0. All right. So it always goes up to the size of it minus 1. So like if you ask for the length, this was called A, this array. What's the length of A? It's 5. Your last index is not 5, but it's 4. Does that kind of make sense? It's always 1 less because they start at 0 like that. All right. And the way to go to a piece of an array is you say its name, and then you say dot item. You say dot item, and then what index you want. So dot item 0 gives you the value at index 0, which is the 8. If you want the second thing, you say a dot item 1, which gives you the thing at index 1, which is the second thing, that's 6. It's the thing living in there at that slot of it. Okay? Any questions about indices? Going to see how that would be useful? It's dot item. All right, and so that's here somewhere too on these pages. Let's find it. Dot item. So you have an array. You say dot item on that array. You go to an index of it. All right. Remember the indices start at 0. So item 2, for example, goes to the third thing, doesn't it? So yeah, if I want the Pikachu out of this Pokemon I like array, that's the thing at index 0. It's the first thing. Go to dot item 0, and then I have Pikachu all by itself to work with, to do things with. All right, so I have that. If I want the second thing, I go to item 1. Then it's happy. And yeah, let me show you some fun math stuff on arrays and some other operations, and I think we'll go from there. There's just some fun stuff to do here. Let's see, and then we'll do a very fun calculated example, and we'll make it work. So that's going to be that one eventually. So yeah, just have a bunch of things to do with arrays, but are we ready to go there? Any questions about the conceptual idea? It's just a place where you can hold a bunch of stuff at once. That's all an array is. And I want to teach you all the operations on arrays now. All right, let's say I've got a bunch of numbers. Let's say I've got, I don't know, an array of temperatures. Let's say I've got a bunch of temperatures, and it might be in Fresno, it might be in other places, like 100 degrees, 78 degrees, 32 degrees, and like negative 40 degrees. So here's a bunch of temperatures in Fahrenheit. I'll call it temps F as an array. And here's a cool thing you can do with arrays. You can say their name, and you can do math on all of them at once. I can say temps F times 2, and what it will do is it will make a new array for me, having multiplied each value, each element is what they're called, each item by 2. So it makes 200, 78 times 2 is apparently 156, but you can do math on arrays by just multiplying or adding a value. You can shift things around, do fun stuff. That's kind of cool, all right? So there's that. There's other things that you can do. We have the len, of course. What's the len of temps F? How many things are in it? There's 4 things, right? There's 4 things in that array. And there's other ways to get at that idea, though. This is all in this array functions and methods here. There's you can read more about them, but I'll just go through them. There's dot size. Temps F dot size is just a little variable inside of the array. It's not a function. It's just a little variable that also tells you how big it is. It keeps track of it itself. So len works, .size works. And then there's other operations on arrays. You can ask it to do things for you. You can be like, there's sum on an array. You can say .sum. You can be like, hey, temps f, what is the sum of all the values in this array? Add them all up for me. That's something you'll want to do a lot. So .sum exists. That's the sum of all those temperatures. There's the average. There's mean is another name for average. Hopefully you've heard that before. But apparently the average temperature of all these in this array is 42.5 degrees. And yeah, there's a bunch of other things that we can do, but they're all baked in like this. I just want to show you a few of them. All right, so shout at me if you have any questions about any of it. But I want to show them to you. Some of them are baked into, because these arrays are really baked into the NumPy library. I will need to import that now if I want to do other cool stuff. So let's get the NumPy library up in here and show you what we can do with it. Yeah, some of these are here, like np, numpy.do something, numpy.do something. So like .diff is the next one I want to show you, but it's part of the NumPy library. So instead of saying import NumPy and then having to say NumPy dot stuff, you can import it with a different name, and that's what the cool kids like to do, apparently. You say import NumPy as np, and so now I can just say np dot stuff, and so people do that instead. So if I say np dot diff, and I give my temperatures array, what it will do for me, it's going to give me an array that's one smaller than the original array. Here's the original array. It's going to give me a size one smaller thing, and what it's going to do is it's going to give me all of the differences. All right, so it's going to be like, what's 78 minus 100? Negative 22. What's 32 minus 7? It's going to do the differences of each of these. It's going to subtract this one and this one, give me the answer. This one and this one, give me the answer. This one and this one, give me the answer. Okay, that's what it's doing. It's always the one later minus the one before. So it's negative 46, 32 minus 78 is negative 46, negative 40 minus 32 is negative 72. It's giving you the differences of all the things next to each other, okay? That's what .diff does, pairwise differences. That's the fancy mathematical way of saying that, okay? So there's that, and with that in mind, I made a temperature Fahrenheit array, and that just screams we should convert it to Celsius. So let me show you how you would do that with your operations on arrays. So let's do that. So apparently, if you start with the way to convert a Fahrenheit temperature, so let's start with the whole thing, is to subtract 32 to convert it to Celsius. You subtract 32 first, and then you multiply every temperature by 5/9. That's the difference. And so that's going to make a brand new array for us of Celsius versions of those same temperatures. All right, because it's going to do the subtract 32 to make a new array, and multiply everything in that resulting array by 5/9. It's going to do the work. And you can save that into another place. Call it like temps C. Celsius versions. So there's that array. And I've now converted all these things to what they should be. Like 32, you better believe that's 0 degrees. Negative 40 is the cool temperature in Fahrenheit and Celsius. It's the same because they're just both lines and they overlap right there. 78 degrees is like 26-ish degrees. 38-ish degrees Celsius is 100 degrees Fahrenheit. So cool. Any questions on how I made that work? You see how you can do math on arrays, and it's going to do math on each element, each piece of it. It's very, very cool. Yeah, the next one is np.round. Is that here? Come here. Sometimes they're in here, sometimes they're not. I just want to show you a bunch of them. So there's np.round. Because this kind of looks ugly. Like it would be easier to read the resulting array if I rounded everything to like 2 decimal places. You can do that. np.round, you give it an array, and it's going to round all the values to a certain number of decimal places, like to 2 decimal places. And that's a cleaner looking array. It's probably more useful for humans to look at. Okay? So yeah, there's that. What else? Yeah, now I just have a bunch of weird stuff I want to show you. But are there any questions about the normal stuff? These rounding things, these are just operations on arrays, and an array is just a chunk of values all at once. Okay? Just a bunch of stuff all at once together. So I want to show you something cool with bools now. So you know that when you do a comparison, for example, you get a yes or no answer. It's true or false. Like 2 is less than 3, yes, so the answer is true. disgustingly, you can do math on Boolean values. You can do math on trues and falses. And true is 1 and false is 0 to Python. I'm going to do something that's going to be very disgusting. True plus false plus true. The answer is going to be 1 plus 0 plus 1. It's going to interpret those things that way. And give me 2 back. Isn't that weird? That's apparently a thing. All right. And the reason I'm saying this to you right now is if you make an array of Boolean values, NumPy is going to convert them to numbers. So make an array of, hey, is 1 less than 2? Is 2 less than 1? Is 8 less than 7? Is 42 less than 43? That will turn into the array 1, 0, 0, 1, because this one was true. True is 1. True is yes and 1. False is 0 and no and low voltage and a bunch of different things inside of a computer. But true is 1, false is 0, and for arrays, it does not keep them as trues and falses. It's making 1s and 0s for you. All right. Because of that, sometimes you have an array of a bunch of comparisons, like I want to know how many of them were true, right? There is a very nice operation on arrays. It's called count non-zero, where it will give you back the number of elements of your array that were not 0. Usually it's going to be a bunch of trues and falses, but sometimes you'll have other values that just happen to sometimes be 0. You say count non-zero. It will give you how many times was it true. How many times was it non-zero? All right. So you can see that it's true twice in this array. You can say np.count non-zero. We're going to use this a ton, surprisingly, in this class. This array of comparisons. There were 2 of them that weren't 0, which means that there were 2 of them that were true. Does that kind of make sense? That leap of logic there? It's weird that it's called that, but that's just how it's going to work for us. It's non-zero, which means it wasn't false. If it's not false, the only other option was true. Okay? So that's why that works. And yeah, I just want to show you a few more, and we'll go from there. So let's go back to that array of Pokemon. It's just a bunch of stirs, right? You can do stir stuff on a bunch of arrays, or on a bunch of array elements at once. You can make them all uppercase, for example. That's part of the np library, np.doCharacterStuff.doUpper. It's the upper function inside of the character part of the NumPy library. It's disgustingly long, but I'm going to give you all this code to study yourself. But here's what it does. It goes and gives you another array with the uppercase function applied to all of those elements, and it gives you them back, as you might expect. There's a dot lower as well. Okay, there's that. And yeah, the last main thing that I care about you understanding kind of right now is there's some special functions inside the NumPy library that generate arrays for you, and those are very, very useful for us. So it's np.arange, and it's here somewhere. This is a very, very important function inside of the NumPy library that we need. It generates arrays for us. There's 3 ways to use this arange function. You can give it 1 thing, 2 things, or 3 things. And what it does is it generates an array for you. Here's the most general way to call it. It makes all the numbers between start and stop incrementing by step. All right? And there's some defaults involved. So yeah, let me show that to you. But the default one, or the easiest way to call it, is to call it with 1 thing. It's going to generate an array for you. So np.arange, it stands for make an array within a range, right? If I say arange 5, it's going to generate the array 0 through 4. So the default starting point, if you don't give anything, is 0. And when you say the stopping point, it's always going to go up to, but not including that stopping point. All right? So that's a little weird to think about, but that's just how it works. So it's going to go up to, but not including that stopping point. If you give it just 1 thing, it's going to start at 0, going up to, but not including the 5. So if you wanted to go up to 99, you'd say np.arange 100. Give you all the numbers from 0 to 99. Up to, but not including the 100. All right? So go back to 5. If you give it 2 things, that's a start and a stop. And it'll increment by 1. So if I say np.arange 10 to 20, it's going to start at 10 now, incrementing by 1, and it'll go up to, but not including 20. See that? It'll generate all those numbers for you, up to but not including 20. That implies then, if I want all the numbers from 1 to 100, what should I put in both of these places? If I want 1 to 100, all those numbers, including 100, what should I put here? Do you see the pattern? If I want this resulting array, I want all these guys, 1, 2, all the way to 100, including 100. Well, it starts at the first one, right? So I better put 1 as the first one. What should I put here? 1 more. Because it's always going to go up to good, but not including that last one. So if I want it to go up to 100, I say 101 there. Because it'll go up to, but not including 101, and the last one then is 100. See that working? Any questions about that? Yeah.
So could you arrange like a string of words to them, like hi to mom?
Oh, that's a great question. I think it's only going to work with numbers. Hi, mom, because it's not very clear on like what comes between those guys. It only is going to work with numbers, unfortunately. Floats and ints. Well, that's a great idea. Maybe when I teach you how to make functions, you can make that yourself. So yeah, that's a possibility. But you have to code it yourself then. Other thoughts, questions? All right. Yeah, the very last way to call it is with 3 things, because sometimes you don't want to increment by 1. You want to increment by like 2s or 5s or something, and that's that one. And I just lost my place, and I'm sorry. I pressed a button. A range. Where were we? There were we. So that's the step part. It's the last thing. It increments by step. So if you want to do it that way, you can count by stuff. So you can be like np.arange 5 to 101, incrementing by 5s. This is going to go 5, 10, 15, 20, all the way to 100. I said 101 there, so that went to 100 and included 100, because if I said 100, it would get to but not include that one. Just only go to 95 again. See that? But it's going by 5s this time. If I want it to include 100, I say 101, go up to, but not including the 101. All right. I could also have said 102 here, and it still would have been fine, because it's incrementing by 5s anyway. Still going to get to 105, right? So anything less than 105 is good here. So I'll just say 101. It's one bigger than the one I care about. You can also use floats, and you can also go in descending order. That's totally fine. You can be like, all right, start at 13, go to I don't know, go to 12, but I want to go. I'm gonna put something here. Go to like 12-ish, but I want to go downwards, so like decrease by 0.1 each time. And because I want to go and include 12, I want all the numbers from 13 to 12 decreasing by 0.1. And if I want to include 12, it's going to go to this but not include it, right? So I want to go down even a little bit farther. Go to 11.9, but don't quite get to it. That's how you have to do it. All right, I hope you see why. This will go down 13, 12.9, 12.8, all the way to 12. If I give 12 here, it will stop at 12 but not include it. Right? I'll go to 12.1. So I go down even one more. 11.9, so it goes to that, but doesn't include that one. All right. So yeah, that's a range in a nutshell. It's a very powerful idea. It's like you give it maximum 3 things, it can give you a very long array, so you don't have to type it out yourself. Okay. Questions about that? Because that is going to be the backbone of a cool example that I stole from the book. So let's calculate pi to a certain amount of precision. Here is a cool way to calculate pi. There's many a formula for calculating pi, but here is one of them. It's this infinite sequence. Maybe you've studied it in a calculus class potentially. It's this idea. If you start with this sequence like 1, you subtract a third, and then you add a fifth, and then you subtract a seventh, and then you add a ninth, and then you subtract 1/11th, and then you add 1/13th. If you do that until the end of time, this part will converge to exactly pi over 4. And then you just multiply what you get by 4 and you get pi. All right. We don't have infinite time on our hands. So let's just go up to the terms that are these, to 1/9999. All right. That'll be enough. That'll be close enough for us. All right. And so what we need to do then is generate this little sequence, or a sequence that lets us build this answer so we can multiply it by 4 and get a good approximation for pi. Okay? So the way that we'll do it, the way that I want to break it down is sometimes, let's see, I'm going to need to use different colors here. Sometimes we're doing subtraction, and then sometimes we're doing addition. You see that? It's like every other, it flips. So let's break down this, this operation, this idea, into the positive terms and the negative terms. So like the positive terms are like 1 over 1 count. You can call this 1 over 1. You see how this is like just a bunch of odd numbers at this point down there. So the positive terms are positive terms of this infinite sequence that we're going to stop at 1 over 99999 at are going to be like these can all be 1 over 1s if you think about it. So these are the positive ones. This one, this one, this one is going to be 1 over 1 plus 1 over 5 plus 1 over 9 plus, it's always incrementing by 4, right? So the next one's going to be 1 over 13, right? 5, 6, 7, 8, 9, 10, 11, 12, 13. 1 over 13. Plus da da da. Does that make sense? That's the positive ones. And then let's also separately get out the negative ones, the negative terms. I'll do a color that's legible. I guess white will work. So like that's minus a third, minus a seventh, minus 11th. Let's just add them all up so we can subtract it all together later. Those can be our negative terms. Okay, those can be our negative terms, and we can go from there. So our negative terms, we can just be like minus the sum of all of them. So like 1/3 plus 1/7 plus 1/11 plus da da da. So all those guys, those are our negative terms. And if we just put a minus out in front after we've added them all up, we're good. So if I add these guys and these guys and multiply the answer by 4, I've got pi. Does that make sense? That's kind of my idea. Okay, that's where I want to go with that. And honestly, I didn't really need either of those pictures. I don't know why I included that, but that's okay. I just really needed that. All right, so let's make this slide prettier then. It's because it's right at the edge. It's unhappy. Let's put it not right at the edge. How about that? So that'll work. All right, so those are the two things I want to do, and we'll go from there. So I want to get at the positive terms and the negative terms. Let's put them as variables. I think that'll be useful. So to get started, let's do the denominators that I care about, right? Because I want to do over all these things, like 1 over 5, 1 over 9. Like let's generate the sequence 1, 5, 9, 13, all the way to 9999. Yeah, does that make sense? Oh, also, I guess I want to keep one of these because I want to go only to 9999. I guess I do have to keep them there. Never mind. So yeah, let's keep them like that. If that's where we want to stop. 1 over 1. And I think that's all that I wanted to say. Yeah, so let's generate 1, 5, 9, 13, all the way to 9999. And I want to do the same thing with 3, 7, 11, blah, 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 all the way to 9999. Those would be the denominators of each of those terms. Okay? That's where I want to start. And we will go from there. Oop, so we're stopping at 9999. And let's make that happen. So the positive term denominators, I'll call it pos denoms, is np.arange. It's going to be the first positive term is 1, right? 1 over 1. So give me the 1. Then next I want 5, then 9, then 13. So it's 1, 2, all the way to 999, including 9999 if it's there. So like let's go to 10,000. All the way there. And incrementing each time by 4. You see it's 4 is 1 to 5 is 4, 5 to 9 is 4, 9 to 13. It's incrementing by 4s. Okay? By 4. That's pos denoms. That will give me all the things that I want to, like 1 over 1, 1 over 5, 1 over 9. I've got the denominator side for the positive ones. Does that part make sense? I want to do the same for the negatives. Those are my positive denoms. Let's do the negative denoms in a very similar way. Negative denoms, negative denoms. The negative denominators start at 3, right? It goes 3, 7, 11, all the way to potentially 9999. It won't. It might include it, actually. So 1,000, just so that we never get there. And it's going to go starting at 3, but it's still incrementing by 4s, right? 3, 4, 5, 6, 7, 8, 9, 10, 11s, incrementing by 4s each time those terms on the bottom there. So those are my negative denominators going all the way there. Okay? Does it make sense how I got both of those? So now I want to turn it into the fractions, like 1 over that, 1 over 5, 1 over 9, 1 over all those things. And then same with this, 1 over 3, 1 over 7, 1 over 11. Then I've got the negative terms, the positive terms themselves. Okay? So the positive terms are then 1 over the positive denominators. Does that make sense to us? It's going to do 1 over all of the values in each of these pieces of the array. It's going to give me back a new array of 1 over each of them. See that? That's positive terms. It's not going to look pretty if I print them. It's going to give me scientific notation, but that's what I want. I want 1 over, like these are denominators, so 1 over each of these, 1 over each of these. So that's my positive terms, same for my negative terms. Negative terms, 1 over negative denoms. I got those values, and again, they look weird. Pos terms, neg terms, they look odd, but the answer now is I want to sum up all the positive terms and then sum up all the negative terms and subtract the negative terms from the sum of the positive terms. Yeah? That's all I want. I want the sum of all these minus the sum of all the negative ones. Yeah? That's what I have right now. So you can do dot sum. You'd be like pos terms dot sum. That'll sum them all up. You could also, there's also a function just called sum. You'd be like sum negative terms. Either way works. There's 2 different competing options here. But I can sum them all up in those different ways. Let's just do, I'll show you the new way. We'll do the sum function, just sums them all up. So I want the sum of the positive terms minus the sum of the negative terms. And that gives me an approximation of pi over 4, right? That's this stuff inside this big parentheses. That's an approximation of pi over 4, and I want to multiply that answer by 4. So 4 times that gives me an approximation for pi, and it is good to only 2 decimal places. We did a lot of work just to get 2 decimal places of pi, but if you do it forever, you do it for like 1,000,000 terms, maybe. You get a few more decimal places. And so that's one way to approximate pi. And it's a great example of how to use this arange function to get a bunch of elements sitting in an array, and we can do math with them. All right. So are there any questions about how I used arange and like the other functions on arrays that we kind of learned about to do an approximation up to that, at least up to 9999 of pi? How we turn this formula into this answer. Any questions about how we got there? It's pretty cool. Yeah, the last things that I want to show you then if we're doing all right are, let me show you this fact. When you have a table, you ask for a column of it, you're getting it back as an array, and then you can do array stuff with it. Because we know we can do some cool array stuff, like sum all the elements, give me the average of all the elements. Like that's data science-y things. Let's make it happen. All right, so let me make a little dividing line to show the progression, and let me include my Pokemon data. So that's in my data folder. It's called Pokemon.csv. Like, I want all the Pokemon and their data, please. There it is. So I'm going to include this one, and we'll look at it together. So I'm going to say table. The way you get it is you say table.read table, and then you say where it is. So this is the file I'm working on right now, chapter 5. My data is in the data folder. So I give as a str where it lives. So data/Pokemon.csv. And then I can assign this to a variable, so I'll call it Pokemon. That's the name of the table I want. And so here is the table. I've just included a table of that Pokemon file, and there's a bunch of stuff. Okay? There's a bunch of stuff. Maybe I just want all the names of Pokemon. There's a column called name, and here's all the names of the Pokemon in order of their Pokemon number. And if I just want those, I can ask for that column out of the table. So if you go to the documentation page, there's a way to find it. You say table.column, then you give the name of it, or you give the index of the column. They start at 0, of course. And it gives you that column as an array. It's really cool, all right? So let me show that to you. And that's different to the idea of selecting, because we've done that before, right? If you say table.select, it gives you a new table with just the columns you asked for. There's a difference. Let me show that to you. All right. So we know already we can say Pokemon.select, the name column lowercase. And this gives me a new table. This gives me just a table with one column, and I can do table stuff on it. The alternative is to say Pokemon.column name. This one gives me an array. I'm getting back an array of all that data. Here's every name of every Pokemon as an array, and I can do stuff with it. I can do like make it all capitals, for example, because it's an array of strs, an array of strings. So like that's the thing, okay? I can ask for columns, and I can do math on the arrays that result from them, or array operations, okay? So here's another column of this table. We've got something that you care about when you're fighting Pokemon against each other is like how strong are they? So there is a, where's their attack? There's an attack value associated with each Pokemon, like how strong are they, kind of. You can ask for that column of the Pokemon table. Pokemon.column, it's called attack. And you can get back the attack values for every Pokemon inside the Pokemon world, and you can call that something. Like here's the attacks array. You're getting it back as an array. All right, here's every value, and you do math on it and be like, all right, what is the average attack of every Pokemon ever? That's the dot mean, right? It's called attacks. That's where I put it. I can say dot mean on it. Apparently, the average attack value on a Pokemon is a little bit over 77, almost 78. All right. There's also a bunch of different ways to ask for the average. Like mean is a way to ask for average. Dot mean exists. You could also say NP. It's in the NumPy library. NP.mean on the attacks array. Like there's a million different ways to do the same thing in Python. Say NP.mean attacks. You can also say NP.average attacks, because average is the same as mean. They gave you both options. You could also compute the average yourself, because what is the average but the sum of all the values over the number of things that are in that sequence, right? That's the sum of everything over the size of the sequence over the len of attacks. Do it yourself. So that's just a bunch of ways to do the same thing. But if you say dot column, it gives you the column of your table as an array of whatever type was that column. Could be strings, could be integers in this case, could be floats, whatever happened to be at that column of your CSV file, that was your data set. And you can do stuff on it that is data science-y stuff. Okay? You can ask questions and answer them. Okay? Any questions about any of that stuff? So that's just a bunch of stuff all at once, but that's sequences in a nutshell. So arrays are the kind of sequence we're going to use in this class. All right, for my last trick, I've got a bunch of miscellaneous things again. So here's one more round of this. Boop. All right, so the last things that I need that you're going to need for assignments based on this chapter are the idea of if you have a sequence, let's say we have a sequence of strings, like 1, 2, 3, they're strings already. So for this example, the sequence already has to be strs. It won't work if it's just the actual 1, the int, 2, the int, 3, the int. They have to be strs already. You can say quotes. It's going to look a little weird. You say quotes, like comma space, for example, will work. And they say dot join. And you put the array within the parentheses of the join function. And let me try to explain what's about to happen. So this is going to be our delimiter, comma space. And we want to join all the values of this array with a comma space around them. This is going to make it pretty for maybe printing out an answer to the user, person who's running your code one day. If I run this, it's going to generate the str 1, 2, 3, where there's space. 1, comma space 2, comma space 3. So it's joined together all the values in this array with a comma space around them. Does that kind of make sense? That's an operation that you'll need one day. And yeah, you can make it work in any way that you want. You can say comma space is a common one. You can be like space and space. So now it's going to take 1 space and space 2. It's going to join them together with that around it. It's always space and space. space and space 3, right? So those are some things. But the sequence had to be strs. If it was just ints, it wouldn't have worked. There's ways to do the conversion, of course, and now you know how. You can call stir on all things. So I think that's most of what I wanted to say about this chapter. Just a lot of little things. Probably the biggest thing I care about you taking away from this chapter is the idea that you can get an array out of every column of a table, and then also this A range is going to come up a whole lot for the rest of the semester. Also, count non-zero, surprisingly, is going to become very important later. Okay, so yeah, that's chapter 5 in a nutshell. It was about sequences. Also, remember that indices start at 0. So yeah, I think that's all that I wanted to say there. We need still another chapter before I can assign more things. So everything, you're still safe without any new assignments for the day at least. Any questions about anything we talked about before I hand it over to you guys to do stuff? Whatever you need to do and ask questions. All right, so let me stop the recording. I'll give that to you.